Okay, welcome back. And now we're going to go on to the next section, 1.2. We're going to learn about describing solution sets. Okay, how do we describe the solution set? So we've dealt with situations where we have a unique solution, right? That one element in the solution. We've dealt with where there was no solution, right? So the solution set is empty. Both of those are easy to deal with. Where it gets challenging is when you have many solutions. How do you describe the solution set when you have many solutions or an infinite number of solutions? So that's what we're going to talk about. So let's use this as an example. Now I gave you one way of showing you, if you remember from the other video, if you're paying attention, I showed you one way to write an ordered pair such that you could describe an infinite number of solutions. But we're going to do another way as well, okay? So let's look at this system here. And let's solve it. So, okay, so now what we're going to do is we're going to take row 1 and we're going to eliminate the x's in rows 2 and 3. So we're going to do 1/2, negative 1/2, row 1 plus row 2, and then we're going to do 3/2. Negative 3/2. Row 1 plus row 3. Okay? So if we do negative 1/2, we're going to get negative 1 here. That'll go away. The y is going to be unchanged. So again, first row is unchanged. The x drops out. The y stays the same. So minus y. And then here we get minus 1/2 minus 1, so that's going to be minus 3/2, right? So negative 1/2 minus 1, yeah, so minus 3/2, and then so this is going to be a negative 3/2 plus 1, which is going to be a negative 1/2. Okay, now the third row, this is going to go away, right? Because negative 3/2 times 2 is going to give us negative 3, which plus 3 is 0. And then here we're going to get, well, this is going to be unchanged, so it's going to be minus y. And then here, what do we get? We get negative 3/2 z plus 0, which is going to be 3/2 z. So it's going to be plus 3/2 z. And negative 3/2 times this. Just want to make sure I don't make a mistake here, right? So negative 3/2 plus 0, so that's going to just give us negative 3/2 z. Negative 3/2 is going to give us negative 9/2. 9/2, yeah. So 9/2 is, negative 9/2 is negative 3.5, so that's going to give us a half, right? Is that right? Yeah. So negative 3/2, that's negative 9/2, oh, which is 4.5, I'm sorry. That's negative 1/2. All right, cool. So now, let me make sure. Oh, this is going to be negative, right? Negative 3/2 times a negative 3/2, so it's going to be minus 3/2. Okay, so now, there we go. Now, what do we see here? We see redundancy. Okay? So immediately, we're going to get a 0 equals 0 here. But let's move on. Okay, so we're going to do negative row 2 plus row 3. And so what's going to happen is we'll end up with what? 2x plus z equals 3. And then we're going to end up with minus y minus 3 halves z equals negative a half. And then in the bottom we get 0 equals 0. Okay, so now what do we do here? So in this case here, what do we have? We've got two equations with two unknowns, but we can't, two equations with three unknowns. And here we can't solve for each one of these. So how do we describe, okay, so we know there's an infinite number of solutions, there's many solutions, but how do we describe the solution? Right? And also notice that not all the variables are leading variables, right? Okay? The x is a leading variable, the y is a leading variable, but the z is not a leading variable. So that means we're going to have everything in terms of the third variable. Okay, and in the previous theorem, okay, remember, we have what? Three systems, right? So remember the theorem that says, hey, the solution will only satisfy this one if and only if it satisfies the final one, because all the different systems are essentially the same, right? They have the same solution set. So if we describe the system, the solution set for this one, it has to be the same solution set for this one. Okay, so now, how do we go about describing the solution set, right? Well, let's solve what we can. So let's start with this one, and so let's solve for y. Okay, so in this case here, what are we going to get? We're going to get y equals what? Negative 3 halves z, negative 3 halves z plus 1 half. Okay? So what does this tell us? It means that, guess what? Z is a free variable. Z can be whatever you want it. So z can be any real number. Okay? But y is dependent on z. But look at this also. X is also dependent on z. So what does that mean? Well, let's solve for x. Let's solve this equation. So we get x equals what? We're going to get negative a half z plus 3 halves. So there we go. We just wrote x and y in terms of z. Okay? So guess what? Now what we're going to do is we're going to substitute in here. So now guess what? Now the order triple becomes what? Negative 1 half z plus 3 halves, comma, negative 3 halves z plus 1 half, comma, z. So this is one way to describe the solution set. Now the other way is to use set notation. Okay, so how will we do that? Well, we do the same thing, but we're going to use set notation. And so with set notation, it would be the set of all solutions would look like this. So the set of all solutions of x, y, and z, such that, what? Exactly what we did here. So x is equal to negative 1/2 z plus 3/2, comma, which is also like an and then y equals negative 3/2 z plus 1/2, comma, and then of course you could have you don't have to have the z, but sometimes you could draw, like you could have the curly brace here, or you could, if you wanted to be, if you wanted to restrict it to all real numbers, let's say, you could say, and z is an element in the reals. And that's it. Okay, now, what else can I say about this? Oh, I can also describe it, instead of this, I can describe it like this too. I could just use the triples, right? So I could say the set of negative 1/2 z plus 3/2, comma, negative 3/2 z plus 1/2, comma, z, such that z is a real number. All right, so that's another way we could do it. I like that. All right. Have a great day.